how do you draw level curves? So remember, we have collapsed it into 2D, so we cannot have Z in there anymore, right? So you find different constants for Z. And then based on these constants, you draw the two-dimensional graph for each of these constants. Now, when you have a map, how do you can't find the three-dimensional plot from your 2D contour diagram or map? How do you do that? You take each 2D plot or 2D graph and you lift it to the level of the constant value of the Z. So therefore, if you have a plot at Z equals 0, then you take that 2D diagram and you put it where Z equals 0. If you have a plot or a graph where Z equals 3, you take that plot and you put it where Z equals 3. And obviously you'll have quite a number of these plots. You put them all together and you get your entire three-dimensional plot. So that's how you get a 3D from a map. All right. And as you can see, the surface of a 3D plot is steep when the level curves are closer together and flatter when they are far apart. So let's draw some level curves by hand so you can see how you draw these maps. Okay? So we first want to draw f of xy equals 4 minus 2x minus y. We will not do many of them. Maybe let's just do about 4, okay? So you can give, so this is your z, all right? You let z be equal to a number of constants. Right, so let's choose some values for z. Let's try z equals 0. We can never go wrong with 0. And you get, when you get 4 minus 2x minus y equals 0. So that gives us y equals minus 2x plus 4. So we have a line actually. Z equals 2. 4 minus 2x minus y equals 2. We have y equals minus 2x plus 2. Do the same thing with z equals 4. That gives us y equals minus 2x. And just let me go up to z equals minus 2. Substitute, that gives us y equals minus 2x plus 6. What do you notice about all of these lines? They all contain minus 2x, so they all have the same slope. Right? So they're all parallel. So basically you're just drawing a set of parallel lines. And so let's just do that. Let's go with y equals minus 2x plus 2. So when x is 0, y is 2. When y is 0, x is 1. So draw a line. Oops. Okay, let me change that 1 here. Unless let me take out this line. I hope it just, okay, that's good. And then label it z equals, which one was that? Z equals 2. Then go ahead, z equals 0 goes through 4. 3, 4, and you just draw the line parallel to that one. And so on. Z equals 4, y equals minus 2x. That goes to the origin. Just draw a line parallel. Whoa. Please, I hope your lines don't look like mine. No, mine. What's the last one? What's the one up there? 6. Just, they should look parallel, okay? That's it. By the way, what do you think the actual 3D plot is going to be? What type of drawing? It's going to be flat, so that's a plane, right? Okay, let's do another one. So that's your Z here. So I'm going to write this as y equals z over x squared. It will be easier to look at. So let me take z equals, yes?
Can you tell what the slope is on the graph from the two-dimensional?
No, now that's a very, very good question. We're going to do that in this chapter, actually. The slope of a 3D diagram is a whole different story. Okay, so we're going to look at that in detail. When we look at directional derivatives. Very good question. Z equals 0 gives us y equals 0. Z equals 1 gives us y equals 1 over x squared. And let's just do z equals 2 equals y equals 2 over x squared. And you see where we're going, right? So we're not going to do any more. We should be able to draw what it looks like. Now y equals 0 is the x-axis, so you need to draw a line. So I'll put it in blue. Oh, let's do a minus. You should always do a minus. Let's do z equals minus 1. Y equals minus 1 over x squared. So let me draw my graph in blue because I need to put that x-axis as part of the graph. You can hardly see it, but that's part of it. Now the first one we have there is 1 over x squared. Now the graph 1 over x squared looks like that. And then what is going to happen is that you're going to have a variety of them. So you just draw a couple. I'm not even going to label them. And then minus 1 over x squared is below here like that. And you're just going to have a couple more, you know. So your level curves are going to look something like that. Okay, so now let's move on to the real stuff. Today we're going to look at limits and continuity of these functions. Now let's go back to two-dimension. Single variable calculus. Remember limits, how we define limits? Let me remind you what it is. Let me just draw a diagram, okay? So this is your y and this is your x-axis. Let's go back to black. Let's draw a function. Let's call it y equals f of x. This is C, and this is L. The function does not have to be defined at C, so there could be a hole in the graph there. Okay. Let me draw a little line here. So that's what you should have seen when you took Calc 1. Okay. What do we mean when we say the limit as x approaches c of f of x equals L? Remember that notation? Maybe a little while ago you did that. How did we describe it? In layman's terms, in the mathematical terms, we use the epsilon delta definition. Remember that? In layman's terms, what we said, if we approach C in either direction, either from the left or right, right? And along the curve, as we get closer and closer to C, the graph f of x gets closer and closer to L, then we say the limit as x approaches C of f of x equals L, right? That's in 2D. In 2D, we actually move from the left and the right. That's the only way we can go, right? Not in 3D. What happens in 3D is that because we are in 3 dimensions, you cannot just go from the left or the right. You have a point, AB, right? And you want X and Y to move towards AB, right? So you can go like that. You can go like that. You can go in any direction. That's the thing about it. And do you remember when we did limits in 2D? Whatever direction you take in the 2D, the left or right, for the limit to exist, the left and right hand limits must be the same. You remember that? So what happens here? We have like an infinite number of directions, don't we? Which is, by the way, within a disk. For the limit to exist in 3D, the limit must be the same as you approach AB from all directions. So you must be saying, okay, how do we do that? There are an infinite number of directions. That's going to take me a long time. There's a method to that. Okay? So I'm going to show you how to do that. But first, let me give you the notation. Definition. The function f has a limit L as xy approaches AB, and this is how we write it. The limit xy approaches AB of f of xy equals L. If f of xy is as close to L as we please, whenever the distance from the point xy to the point AB is sufficiently small but not 0. Okay, so that is basically the definition of it. That's a layman's definition, by the way. Okay, as we approach AB in any direction, f of xy approaches L. That's the definition of a limit. That's another notation that you may see and that you may use. Now let me give you the mathematical definition. I will give it to you. It's a very difficult definition. We will only use it once. I will just do one example and leave it alone because it's very difficult. We say that this limit is equal to L if, remember this epsilon thing? Some of you may not have seen it, but I know my students saw it. If for every epsilon greater than 0 there exists a delta greater than 0, such that f of xy minus L, its absolute value is less than epsilon whenever this. What is all of this saying? This first inequality just explains that the function approaches L. Epsilon is just a tiny number. That's all it is. Okay? What is this square root thing and all of that's the equation of a disk or a circle. So this disk has radius delta. The center is AB. So this is exactly what I drew a while ago. AB, radius is delta, and we are approaching in many directions. That's what this means. And why do I have this greater than 0? All this is saying is that the function does not have to be defined at AB. That's why you have this greater than 0 there. All right, let's do some limits. The limit laws apply here. Remember the limit laws. And we're going to go over them, okay? So we're looking at substitution. We're looking at squeeze theorem and all of that. So that is something you need to go back to your Calc 1, but we're going to do it again anyway. Now, it is easy to show. I'm going to first start by looking at limits that don't exist. If a limit does not exist, why? It's because somewhere, using one of the directions, we get something that is not unique. Okay, remember that the limits must be the same in all directions. So I'm going to show you, first of all, how you show that the limit does not exist. So that means we have to get one place where we have a difference. Okay? Then I will show you how you show that a limit exists, which is a little more difficult. Okay? All right. So let me show you I have listed the methods for you, and then we'll do examples. What you do, you substitute. Okay? You just do ordinary substitution. If you get indeterminate form, remember what indeterminate form is? 0 over 0, infinity over infinity. Right. Then you use the procedures. The first procedure is iterated limits. So you take it a bit at a time. So you take the limit as y approaches b, then you do limit as x approaches a, and then you switch. If they are unequal, then the limit does not exist. If they are equal, don't say the limit exists. That's just along one direction or two directions. Remember, they are an infinite number. So if they are equal, further testing is necessary. What do? Check on another direction. So number 2, find the limit from different directions. And what directions do we use? You can go along a line. You can go along a curve. Okay? So, and I will show you how you choose the lines. The important thing, if you want to show that the limit does not exist, you must find one place where you don't have a unique value, and you're done. Okay, let's do some examples. Show that the limit does not exist. And I will phrase it. Show that the limit does not exist. So that means you have to work to find a place where you don't have a unique limit. The limit as xy approaches 0, 0 of x minus y over x plus y. Substitute. Put 0. What do you get? 0 over 0, right? So the first thing you do is to take iterated limits. So set it up. The first direction, put the limit as x approaches 0 outside. Put your parentheses. Put the limit as y approaches 0 inside. And put the function. So what you do, you take care of what is in the parentheses first. Okay? So equals, put your limit as x approaches 0 on the outside. Deal with that last. Now do this limit. How do you do this limit? Just substitute. Put 0 for y. What do you get? X over x. Which is limit as x approaches 0 of 1, which is 1. Any questions here? Okay, now switch them around. So we got one direction, switch them around. So put the limit as y approaches 0 on the outside. Put the limit as x approaches 0 on the outside, and put x minus y over x plus y. Equals, leave the limit as y approaches 0 on the outside. Put x equals 0, what do you get? Negative y over y, which works out to be negative 1, which is equal to negative 1. What do you notice? The limits are different. The limit doesn't exist. So the limits are not unique. So the limit does not exist. That's the first one. Any questions here? Right, so let's do another one. Yes.
You say it's not unique.
Because 1 is not equal to negative 1. That's what I mean by not unique. They have to be the same for you to continue. Okay, so important theorem about limits are that they must be unique in that for them to exist, they all have to be the same limit. in whichever direction. Okay? Okay, so number 2, if you substitute 0 and 0, you get 0 over 0, right? So you always try with your iterated limits. Always start there. Okay, so do the same thing we just did. Put your limit as x approaches 0 on the outside. Put your limit as y approaches 0 on the inside, and your function. Put y equals 0. That gives us 0, right? That's 0. Okay, switch. Limit as y approaches 0. Limit as x approaches 0. 2xy over x squared plus y squared. Put x equals 0. We get 0 again. Answer is 0. So the limit is unique, right? No conclusion. Please do not say the limit exists, because that is only along two directions, right? Let's try along a line. Now, how do you know which line to choose? Look at, okay, so let's say try along a line. How do you know which line to choose? Look at the limit. It says xy approaches 0, 0. So you look at a line that passes through 0, 0. Give me one of the most popular lines that you know. Give me an example of a line. Y equals x. Yeah? Well, that passes through 0. Any y equals 2x, 3x, 4. All of these pass through 0. Right? So try along a line. So let's say y equals x. And put a reason, because it passes through 0, 0. Right? Just in case you can't remember why we chose that line. Okay, so when you do that, how do you do that? You just substitute. So when you try along a line, you're going to rewrite the function so that it's a function of one variable. So in other words, you're going to substitute y with x. So this is what you're going to get. So the function is going to be, this is the function, so instead of y, put x. So it's going to be 2x squared over x squared plus x squared. Alright? And so you're going to have the limit as x approaches 0. So it's just in terms of x. Okay, now simplify that. What's that? That is 2x squared over 2x squared, which is, the answer is 1. And here we stop. Why? Why do we stop? Why are we finished? It's not 0. We got something that's different, so we stop. All right? If we got 0, then we'd have to try it along a curve. Okay? So we say, since, let me just say 0 is not 1, the limit does not exist. Now let me show you, we have a little space down there. Let me show you another method that you could have just done it in one line. Method B. Some people, they just look at this right away and they see that is going to give 0 if I take the iterated limits, right? So you can just go along a line right away, but make the line general. So instead of going along y equals x, you can just go along the line y equals kx or mx. Make the line very general. So you can just say, go along line, say y equals mx. So instead, in place of y, substitute mx. because the line y equals mx passes through the origin, right? For any value of m. Good? So it's going to be the limit as x approaches 0. Okay, what's the thing again? What's it? 2xy. So it's 2x times y mx over x squared plus, so that's mx all squared, right? Simplify that. That's the limit as x approaches 0 of 2mx squared over x squared plus m squared x squared. I'm going to continue writing like that because I don't have much space, okay? So equals, now you can factor x squared from the bottom. Then cancel the x squareds. 2m over 1 plus m squared. And I hope you notice that this is a constant, right? There's no x in there, so your answer is just 2m plus 1 plus m squared. But m can be anything, right? Remember, m can be any value. So depending on the value of m you put there, you will get different answers. If I put m equals 1, what do I get? 2 over 2, which is 1. If I put m equals 2, I get what? 4 over 5. So already the limit is not unique. So you can just say which depends on m. So the limit doesn't exist. Excuse me. So my point is that you can just take that route. Just go along the line y equals mx, and then that would be enough. Let's do another one. Two x squared y over x to the fourth plus y squared. Iterated. Always go for the iterated limits. Let's do it. Limit as x approaches 0. Limit as y approaches 0. Of 2x squared y over x to the fourth plus y squared. And this is going to be 0. The other switch. Limit as y approaches 0. Limit as x approaches 0. Of the same thing. Gives me 0. No conclusion. We're going to try along a line. Let's be very general. Let's just try it along y equals mx. Right away. Try along y equals mx. Okay? So this becomes the limit as x approaches 0 of 2x squared times mx over x to the fourth plus y squared is m squared x squared. Now let's see. At the denominator we can factor out x squared. So as the limit as x approaches 0, numerator is 2mx cubed over factor x squared plus m squared. I can cancel the x's. So, well, the top is x cubed, so at the top I'll have 2mx over x squared plus m squared. Now, notice that we still have x in there, so you can substitute 0 for x. What do you get? 0. What? Do we stop? No, we can't. We still have zeros everywhere. What do we do now? Along a curve. Beautiful. Which curve passes through the origin? Y equals x squared. Yeah? By the way, that's not the only curve that passes through the origin. There are a number of them. Y equals x squared. X equals y squared. Y equals x to the fourth. You see where I'm going with that? X equals y to the fourth. You may be wondering, okay, when will we end, right? Okay, so let's try along y equals x squared and let's hope it works, okay? Along y equals x squared. So limit as x approaches 0. So in place of y, we're going to put x squared. 2x squared times x squared over x to the fourth plus x to the fourth. What do we have here? 2x to the fourth over 2x to the fourth, which is equal to, yay, we're done. 0 is not 1, so the limit does not exist. Now, you know, with practice in doing this question, I would have known that y equals x squared would not work. Because if I look at the function, I see the presence of x to the fourth, I would put y equals x squared. Okay. Okay, try this one. We're going to do them together because some of them can be quite difficult. Try this one on your own. Try the iterated limits first. Okay, you should be finished that. What did you get? What method did you use? You did it along a line right away? Wow. Was it necessary to do it along a line? What did you do? The iterated limits worked, right? Let's do it. Limit as x approaches 0. Limit as y approaches 0. X to the fourth minus 4y squared over x squared plus 2y squared. What does the inner limit give you? When you put y equals 0, what do you get here? X squared, right? X to the fourth over x squared, which is x squared, and that gives us what? 0. Switch. Along, put x equals 0, what do you get there inside? Negative 2y squared. Okay, let's work it out. So when you put this, you get negative 4y squared over 2y squared. Okay, now, by the way, always simplify, right? When you simplify, what do you get? The y squareds cancel, don't they? So you're left with negative 2. You're done. Okay? So you didn't have to do much here. Try that one. The clue there is the y to the 8th. You need to check the iterated limits because you need to have something to compare it to. But if you check it out, you would be able to know what to take it up. Because I think the last example we did when we took it along the curve, we saw x to the fourth and we try y equals x squared. So you see y to the 8th. Let's see what you would try it along.
Yeah, that's what I did.
Let's go. Let's try something here. So you try the iterated limits. What did you get? 0, 0, right? So let me just write it down. That's 0. That's 0. You want to go somewhere where you do not get 0. If you try it along a line, it's going to be 0 too, right? If you try it along y equals x squared, it's going to be 0 too. Any suggestions?
X equals y to the fourth.
X equals y to the 4th. You see what I mean about trying? you just have to try these things. And how would I know that? The presence of y to the 8th told me that. Okay? So try along x equals y to the 4th. So this time, everything is going to be in terms of y. So go y approaches 0. So replace x with y to the 4th. X squared is now going to be y to the 8th. So this becomes y to the 8th over 2y to the 8th. Simplify that. You get 1/2 where y to the 8th cancel. And your final answer is 1/2. The limit does not exist because 0 is not a half. The limit is not unique. So that's a procedure for showing that limits do not exist. Any questions? Now, believe it or not, it's easier to show that the limit doesn't exist. How do you show that they do exist? Because for them to exist, right, for every single direction you must get the same limit, right? But there are an infinite number of directions. How do you deal with this? Okay, we're going to look at a number of things. Number of tricks. Substitution. If you substitute and you get a definitive answer, you're done. Alright, you don't get indeterminate form, you get an answer, you're done. The limit exists. That's the easiest one to go by. Sometimes you can factor the numerator and denominator and reduce and then substitute, and it works out, you're good. So these are the easiest ones. Then you can use the squeeze theorem, which we will go over in a little while. The fourth one is a very popular one. And from experience in teaching this course, a lot of students seem to like this one. When substitution does not work, they use the polar coordinates. Why? Because circles, remember we are looking at within a disk, approaching AB within a disk. A disk is a circle. Circles are defined by polar coordinates, right? So if you can write everything in terms of polar coordinates and then find the limit as r approaches 0, if it's xy approaches 0, 0 that is, as r approaches 0, that makes it a lot easier for you. So I think in all of these, if the substitution number 1 and 2 don't work, I would head for this one. Let me put an asterisk by that. That I think is the easiest one. This one. But you must try people always forget to substitute and they just go for number 4. Do number 1 and 2 first. If they don't work, then head for number 4. Okay? Number 5, I would not even do that. I mean, I'm going to do an example for you to show you how hard it is. That's the only reason I'm doing it. Okay? Right. All right, let's show that some limits do not exist. All right, so I really should have shown you an example of substitution, you know. Let me just show you an example. quickly. I'll just put an example here. If I give you the limit as x, oh no, that's an example. I'm sorry, I was looking at something else. Don't write that. It's right there already. Let's do that. Okay, always try substitution. What do you get when you substitute this? So put x equals 1 and y equals 2. What do we get? That's 4, right? Over 1 plus 4, 4/5. Done. Don't go anywhere else. You're done. Okay, you finished. The limit exists. It's 4/5, right? So as I say, always do that first, or else you will be wasting precious time. Good? And as I say, people always forget about this. Okay. Now we're going on to the tricky ones. Okay. So again, I could, number 2, if you substitute, you get 0 over 0, indeterminate form. You need to go to the other methods. You cannot factor anything there. So you either do the polar coordinates, the squeeze theorem, or the epsilon delta definition. By the way, all 3 will work. They will all work. If you notice, I think I have 3 examples there, so I'm going to show you one for each of them. So for this one, I'm going to show you the polar coordinates one. So we're going to use polar coordinates because this is the most popular one. It always works well. So you just substitute x equals r cosine theta, y equals r sine theta. And let the limit of r approach 0. So you have limit r approaches 0. So let's substitute. So this is r cosine theta times y squared, r squared sine squared theta, all over r squared cosine squared theta plus r squared sine squared theta. And what you should try to do is to simplify this as much as possible, okay? Now, factor out this r squared from the bottom, and we need to bring the r's together on the top. So r cubed cosine theta sine squared theta over r squared times cosine squared plus sine squared. We can cancel some r's here. And what do you notice at the bottom? That's 1. So when we cancel out this r's here, we're just left with r cosine theta sine squared theta. Any questions so far? So the limit is what? 0. Done. You're done. Okay? So that's why I say this is really the easiest one. Any questions on that? Next. Now this one, you could also use the polar coordinates method here. It will work very nicely, but we're not going to use it. I'm going to try the epsilon delta definition. And I am actually going to put in parentheses HARD. I do not advise this. Okay? And how many of you, let me just see a show of hands, did the epsilon delta definition in Calc 1? No. It's only my students.
Yes, you
Oh no, you did it.
we might have done all the
It's a very difficult thing. So sometimes it's not taught. So I'm not going to go over this from Calc 1. It's going to take me an entire lecture. So I'm just going to do it. All right. So you start, let epsilon greater than 0 be given. We need to find a delta greater than 0 such that. Okay. So what you do, you go back to the page where I gave you this epsilon delta definition, and you just plug in what this is our f of x here. Plug in your f of x. Your a and b are your zeros. Okay? So you just look at the definition. So the definition says the absolute value of f of x, 2xy squared over x squared plus y squared. Okay, I should have phrased this question another way, because if I have to use the epsilon delta definition, I actually have to give you the limit. So rephrase this and say prove that the limit is 0. The limit is 0, but I want you to prove it. Right. Okay, so the definition says f of x minus the limit, which is 0, less than epsilon, whenever 0 is less than the square root of, and what we had was x minus a all squared plus y minus b all squared. A and b are both 0. So this becomes x squared plus y squared less than delta. Now, what you're trying to find is delta in terms of epsilon. And the way you do that is that you need to match. You need to reduce this thing, this absolute value thing, to this. Square root of x squared plus y squared. That is why this is hard. Because you say, what is the relationship between these two? I cannot see anything that makes sense. Okay? So it's a lot of hard mathematics, but I'm going to do it for you, as I said, just to show you that it's hard. And that is why I don't want you to go there. It's a lot of trial and error. So, y squared, follow me, is less than or equal to x squared plus y squared. Agreed? So this implies divide both sides by x squared plus y squared. Y squared over x squared plus y squared is less than or equal to 1. I just divided. And you may say, okay, why am I doing this? Because you see this little thing, the x squared plus y squared is at the bottom. So I'm getting there, right? So absolute value of 2xy squared over x squared plus y squared is the same thing as 2 times absolute value of x times y squared over x squared plus y squared. That's what that is the same thing. But we know that this thing has less than or equal to 1. So all of this is less than or equal to 2 times absolute value of x. But absolute value of x is the same thing as square root of x squared. That's a definition of square root of x squared. Which is less than or equal to 2 times square root of x squared plus y squared. Which is less than or equal to, from up here, square root of x squared plus y squared is less than delta. So this is less than or equal to 2 delta. So this says that all of this is less than or equal to 2 delta, and we also said it's less than epsilon. So we choose epsilon equals 2 delta. And so delta is epsilon on 2. That's the proof. Okay?
I'm using that bad boy all the time.
Yeah.
Is that
You
right?
can't use that?
You should. Why don't you dream about that tonight?
Are you gonna ask us that?
No.
That was quick.
What happened? No, 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 no. That is just for your information. Just wanted to show it to you.
What was your other thing?
Number 4. Yet another method. The third one that let me tell you, polar coordinates will work for that. Always go for that. It's easy, right? Epsilon delta definition will work for that too, but don't go for that. It's hard. Squeeze theorem would work for that. The squeeze is a little challenging, but not as challenging as epsilon delta. What is the squeeze theorem? Let's just remind you. You take the function you have to find the limit of, and you squeeze it in between two functions that you can find the limits of easily. Right? Now, these two functions on the outside, it's like a sandwich, right? You have the cheese inside the two slices. The cheese would be the function you have to find the limit of. The two slices of bread are really easy functions that you can find the limit. But the key thing is that the limit for these two functions must be the same. And if they are the same, then the limit of the function in the middle, which is the cheese, will be that same limit. So the key thing is to find these two functions. A good function which always works for the left is 0. Always. If you can get a function on the right which has a limit of 0, you're good. But the thing is, you have to be careful because it is an inequality you're looking at. Okay, the squeeze function, as I said, the function must lie between 2. So you need inequalities in between. All right, let's see what we're going to get here. So we need to look at this. Put absolute value. Absolute value always helps with these things. Try to see what you can do to manipulate this function. Now, look at this function. This function is always greater than 0, isn't it? That's why I use the absolute value, you know. Absolute value is always positive or 0, right? So we know that it's always greater than or equal to 0. We have something on the left already. We need something on the right. Okay? What function is this less than? Okay, simplify this. This is the same thing as x squared over x squared plus y squared times absolute value of y. Why didn't I put the absolute value over this square? Because they're all squared. They're positive. It doesn't matter, right? So I just put the absolute value over the y. This is less than or equal to x squared times absolute value of y over x squared. Why? X squared plus y squared is bigger than this x squared thing. So this fraction is a smaller fraction than that. The x squared cancels out, so that's equal to absolute value of y. We have that this here is less than or equal to absolute value of y, but greater than or equal to 0. Now you check the limits. The limit as xy approaches 0, 0 of the function on the left 0 is 0. The one on the right now. The limit as xy approaches 0, 0 of absolute value of y is also 0. So the squeeze theorem says, so the limit as xy approaches 0, 0 of x squared y over x squared plus y squared is also 0. Done.
Can you move that up a little bit?
Right. Up to where you want to go.
No.
Just
So it's the bottom of
The
it.
part that you scroll up.
Oh,
Thank you.
oh, sorry. That's the squeeze theorem.
Can you always use 0 on the left?
If you put it in absolute value, you can always use 0 on the left. That's why when you use squeeze theorem for these type of functions, put them in absolute value. Okay? Any questions so far? Any questions on limits? Okay. Continuity now. Continuity, remember, in single variable calculus, you don't have continuity when there is a hole somewhere where the function is undefined, right? In multivariable calculus, these three-dimensional figures, if you have a hole, obviously, you can't have continuity there, right? But if you have something like a steep corner, right, that's what happens. The function is discontinuous at that corner. So that's how you recognize it from graphs. How do you deal with it mathematically? This is the definition. A function f of xy is continuous at ab if the limit as xy approaches ab of f of xy is equal to f of ab. That's the definition of continuity. Thus, oh, that should be a thus, not a this. Thus, three conditions must be satisfied for continuity. The first condition, the limit must exist. The next condition, the function must be defined at AB. And the third condition is that the limit must be equal to f of AB. If any of these conditions is not satisfied, the limit doesn't exist. Okay? But all three of them must come to, what did I just say? Let me go back. If any one of these conditions is not satisfied, the function is discontinuous at AB. They all have to come together for you to have continuity. Okay? So let's look at a simple example. F of xy is equal to 3xy when xy is not 1, 2. There's another error here. I'm so sorry about this. And 0 and xy equals 1, 2. Is f continuous at 1, 2? We go through every condition. So the first thing, let's find the limit as xy approaches 1, 2 of f of xy. That is equal to the limit as xy approaches 1, 2. We choose 3xy because it's approaching 1, 2. It's not equal to 1, 2. And you can just do this limit by simple substitution. And that is equal to 6. Put x equals 1 and y equals 2. Right. So the limit exists, right? Move on to the second condition. What is f of 1, 2? From the definition of the function. It's 0, right? So the second condition holds. The function is defined at 1, 2. But what do you notice? 6 is not 0. They have to be the same for continuity to occur. All right? So since the limit as xy approaches 1, 2 of f of xy is not equal to f of 1, 2, f is discontinuous at 1, 2. Any questions?